Can you, yeah, thank you, sweet. So yeah, I am going to be talking today about formal verification of EVM bytecode. Thanks all for making it this far. This is the last talk, I think, pretty much, so yeah. Academic grants program as well. So yeah, formal verification, well, what do we want to do? So we want to show something is true for a sequence of bytecodes or possibly sequences of bytecodes, right? And well, what something would we want to show? Well, there are different kinds of properties. Like here's a sequence of bytecodes. What kinds of things might we want to show about it? Well, we might want to show, for example, that there's no arithmetic overflow or underflow. That's a real simple property. We might want to show something different. Maybe we've got two sequences of bytecode. One is the optimized version of the other. And we want to show that after executing them, the EVM is in an equivalent state, right? So that it's really a true optimization of the original sequence, right? Maybe a more complicated property if we're doing a token contract. Like maybe we've got a map from addresses to balances, and we've got like a total field which counts the total number of tokens in circulation, and it should be a sum of all the balances in my map. And I want to show that, yeah, no matter how I execute my contract, this sum, this total, is really a sum of all the balances. Well, there's lots of different ways that we can try to do this, right? So, we can try to use fuzzing and testing, and that's a pretty effective way of approaching this. We can write some assertions which will be checked at runtime. We can run the fuzzer, and if it trips an assertion, then we found something. But the challenge with fuzzing and testing, it's not a guarantee. It's not exhaustive. It won't check every possible input. So there may be some edge cases left that it hasn't tried. Another approach is to use a static analysis, which we're sort of talking about a little bit in the last talk, right? We can run a static analysis. It's also an effective way of working. It's typically a push-button tool. We run the analysis. It gives us a result. But we typically are limited in what kinds of things the analysis will actually look for and what it'll check for, right? And so, for example, checking that our total in our map, is a total of a sum of all the balances in our map, is probably not something a static analysis is going to check for. So we're looking for something which is a guarantee. It's going to give you a guarantee. We can write flexible properties that we want to check, and that works, right? And so yeah, that's what we're doing. So let's have a look. So I'm going to talk a little bit about the Daphne EVM. So this is a model of the EVM that we've built. We've used this programming language called Daphne, which is, we'll see a little bit of it later in the talk. Daphne is the verification system that we're using. And so yeah, it's an EVM. It's written in Daphne. It's not a full client. We haven't implemented everything, right? It's also fixed on Berlin at the moment. We could support other forks, but for now we're just keeping it simple. And we've implemented the semantics of all instructions that are supported in Berlin and some others, in fact. The model is executable, so I can actually execute this bytecodes through this EVM and see the state afterwards, right? And I can run tests, as we'll see. It is gas accurate as well, although it's not very relevant for this talk. So I guess the key thing here, is that this Daphne verification system, it doesn't know anything about EVM. It's not designed for the EVM at all. It's just a verification system. So we need to tell Daphne what the EVM does, what bytecode instructions should do. And so this is what our Daphne EVM model is doing for us. We're encoding the semantics of all these instructions so that Daphne knows, what they're supposed to do, and we can use that model to then verify sequences of bytecodes. So here's just an example, a Daphne function. I haven't got a lot of time, unfortunately, to go through all the aspects of Daphne, but just to give a kind of taste here. So this is the semantics of the add instruction inside our model, right? And so at the very top, we can see the parameters. We're going from an executing state of the EVM, and it's producing another state, right, which is an updated state. Now, that might be an executing state, but it could also be like a reverted state or an exception, for example. We've got these ensures clauses. Now, those are the post conditions for this function. And so we can think of them as a sort of summary of what the function does. And the key thing about Daphne is that it will check for us at compile time that those post conditions are true for the implementation of the function. right? Which is, that's quite different from most programming languages. So in this case, let's say, like the second ensures clause, it's basically saying, after the add instruction, if the EVM is still executing, then there must have been at least 2 operands on the stack, right? Otherwise, we would have had an exception, right? And if we look at the body, it's reasonably straightforward. We're taking 2 items off the stack. We're adding them together. I've got an explicit modulus here to 2 to the 256. That's because arithmetic in Daphne is unbounded. It doesn't have, overflow or wraparound semantics. So I'm modeling it here. And then I just basically push the result onto the stack, increment the program counter, and so on and so on. So yeah, we've implemented functions like this for all of the bytecodes, all of the EVM bytecodes. Obviously, some are a little bit more involved, and others are simpler as well. Okay, so we've got this model of the EVM, but I suppose the question is, well, how do we know it actually is the same as the EVM? Like, how do we know it reflects the EVM, right? Like, is it a good model? Is it right, And so to answer that, we've used the Ethereum common tests. And so what we've done is we compile our model into Java. We've got a little test runner that basically runs all the Ethereum common tests through our model, right? So there's about 13,000 common tests for the Berlin fork, and we've selected 7,500 of those. Now, there's a number of tests that we don't select for various reasons. The biggest reason is that there are a whole load of tests in the time-consuming folder that take a very long time to run, and I just haven't run them. Some of them may well pass, in fact, but I haven't run them all. Another reason is that we don't support everything. So, for example, we don't support type 2 contracts. There are certain precompiles that we don't support, and so on and so on. And so then we run that and we compare them against Geth. And so we're not just comparing the output, but we're comparing the state after each instruction is executed, the state of the stack, and so on, making sure it's identical. And so of the ones that we've selected, we've got about 96% passing. Some reasons why bytecodes fail include we don't actually have a check that you can't branch into an operand of a push instruction, for example, right? I mean, I could add that check, okay, wouldn't be too hard. This basically just gives me the idea that, yeah, we could get all the tests to pass if we wanted to put in enough effort. It's a pretty accurate model. For now, for me, that's good enough for now. I'm more interested in actually using the model to verify code than I am in spending, more and more time trying to make it accurate. Cool. Okay, so that's the model. So what I want to do is, look at some examples of actually verifying things using the model. That's what it's about, right? So yeah, this is a proof, right, in using the Daphne EVM. And what I want to show here is that we've got 2 sequences of bytecodes. One is an optimized version of the other. And so if we look, we can see the sort of middle 3 bytecodes there, the push 1, add, right? So that's my original sort of code sequence. I'm pushing a constant m, I'm pushing a constant n, adding them together, right? Now we know they're both constants, so we can actually pre-compute the result. And so then we can just push the 2 constants added together onto the stack. Now, there is an issue here, actually, because, of course, I'm using a push 1 bytecode, so if I add those 2 constants and they overflowed, well, there would be a problem, right? It wouldn't be equivalent. So in fact, I write a precondition for my proof, which is the requires clause. And the requires clause says, if we add these 2 things together, they don't overflow. So with that assumption, these 2 code sequences are equivalent. And that's essentially what we're saying down the bottom. That assertion, the Daphne system will check for us at compile time, and it will tell us, in this case, yes, I'm happy that's right. Now, they're not going to be identical, because, of course, like the program counter, for example, will be different. So they have to be equivalent. And in this case, that means, the stack has the same stuff on it, memory has the same stuff, storage has the same stuff, right? But there can be some other minor differences, program counter in particular. So a slightly longer example, just to illustrate a few more aspects of how it works. So this is a complete contract. It's a counter contract. So whenever we call the contract, it increments this counter, which is stored at storage location 0, just increments it by 1. If, in a highly unlikely event that counter should ever overflow, then it will revert. All right? And so we've got kind of 2 paths of control through this bytecode sequence. And so what you can see here is that I've represented the control flow using sort of statements of the Daphne language, right? So I've represented it using the conditional if-else of the Daphne language to separate out the two paths of control flow, right? And at the very bottom, the assertion that I'm checking in this case is just that if the contract executed successfully, i.e. it didn't revert, then our counter has actually increased. Right? I could have shown that the counter had increased by 1, but in this case, I'm just showing it's increased, right? And so again, we can prove that that is true for all executions. Cool, okay. So that's 2 really simple examples. Obviously, we want to verify properties on more interesting contracts. I don't want to have to write out, the contract by hand, the bytecode by hand. I don't want to have to do that. So I need a tool that is going to take contract bytecode and generate one of these proofs for me. Okay. So that's the proof generation tool. And so in this case, I'm taking a contract written in Solidity, I'm compiling it with Sol-C, and I'm getting some bytecode. Now, it doesn't have to be Solidity compiler. It doesn't really matter how I get the bytecode, actually. It could be Viper, or it could be just bytecode taken off chain. So once I've got the bytecode, I'm going to run it through this Daphne proof generator tool, and it's going to generate a Daphne proof for me, which is basically a collection of 1 or more Daphne files. And those files, they probably won't verify to start with. Initially, they're not going to verify. What needs to happen is that I need to actually sort of manually tweak the proof so that it will verify, right? So I need to do certain things to help Daphne and to make it realize the proof is correct. And the Daphne proof generator is doing a lot of stuff. It's doing a bunch of static analysis for us. It's lifting out the control flow graph, and it's splitting up the contract into different files and all this stuff to sort of help reduce the amount of work that I have to do as the user. So here's an example. This is a betting contract. Again, it's a pretty minimal Solidity contract, but it illustrates some aspects of it. It's compiled with optimization enabled in this case, which gives us about 195 bytecode instructions, which are split by the proof generation tool into 37 8-instruction blocks. We split them up into blocks to effectively reduce the loading on the Daphne tool. And the property I wanted to verify is that there's no arithmetic overflow or underflow. You can see in the contract I actually have an unchecked block. So in principle, it could overflow or underflow. We can see by looking at it that it doesn't. But the goal is to prove, it doesn't, right? That's the goal. And so I had to make 12 manual interventions in this case to make it verify. And so the interventions, sort of different kinds. So for example, in some cases, there are things that Daphne should be able to prove, so blocks that are correct, but for some reason the tool won't prove. The SMT solver will time out or something like that. And so then I have to manually insert these sort of intermediate assertions to help it. Also, for example, there's an instruction. So in this particular contract, it uses a subtract operation as a sort of optimized equality test. And so it's actually expecting that it could actually underflow and so on. All right, so we have a look at the actual, this is sort of the output from the proof generation tool, maybe if I get out of the way. And so what we can see firstly is that the static analysis has put in comments a whole bunch of stuff about the stack. So it's telling us, the constant values on the stack that it knows about at each location. If it's got an underscore, then that just means it couldn't figure out anything about that location. That's fine. The primary reason for putting this in as comments is just to help me when I want to do a manual tweak, to help so I know where stuff is on the stack and I can do that tweak more easily. The other thing we can see is that the underflow check here is this assert. That's added automatically by the tool. And so that's really what we're trying to check. We're trying to check that that assertion is true. And it's telling us that the thing we're subtracting from is bigger than the thing being subtracted, right? And the final thing that we can see up here is the precondition that I've marked added by me. And so that's a precondition that I had to add to help Daphne prove this assertion. And that precondition is saying in this case that what's stored at location 0 is greater than the current call value. Now that's something that was established by a conditional sort of further up in the contract. And so it's established at some block further up. But my static analysis couldn't figure that out, so I've had to manually propagate that information down, and with that, it will then verify this block. Cool, okay, so the last bit. Wrapped ether. So, okay, the betting contracts were still quite pretty artificial still. We wanted to look at a real contract. And so we've taken the wrapped ether contract off-chain, It's about 6.5K. It's actually unoptimized. The bytecode is completely unoptimized, which means it looks terrible at times. It was compiled with Solidity 0.419, which has some effect. So for example, the free memory pointer is at Nordex 60, not Nordex 80, which confused me for a while until I realized that was a thing. But otherwise, it's fine. Some instructions are unreachable as well, which is fine, but just confusing. And I guess I should say at this point, basically, this is in progress. This is something I'm working on. It does present many challenges. For example, it has loops, and we have to show termination. And it just generally pushes Daphne quite hard. And yeah, it hasn't been a bed of roses, but we are making progress. So yeah. Cool. And that is about me. If I don't know if there's time for questions, but if we don't have much time, feel free to find me. I'm here all week and just ask me a question. There is also a paper that you can find online where we talk much more about the Daphne EVM. Cool, thank you.
We technically have 10 minutes until the closing ceremony starts, but if there are any questions, then now would be the time. Aha, we have one. This is how it starts.
That unreachable code in wrapped ether, was that actual code, or was that in the data segment for the signatures that looked, acted, and smelled like code?
So it's a question of how you, it's debatably unreachable. So the wrapped ether contract has, I think it's just the name, wrapped ether, which is a constant string, wrapped ether. But the contract is compiled to work for an arbitrary string at storage location 0. And so that means because wrapped ether is like less than 32 bytes, it fits into a small string format as opposed to a larger string format, but the actual contract code supports both. So there's just a whole massive chunk of code that just isn't used because that particular constant string has a fixed size. Does that make sense? Yeah. So in theory, you could launch the contract with a different string, I suppose, but that's not what the contract is supposed to be. Yeah.
I just wanted to point out that once we have EOF, some of those checks will go away.
Yeah, I mean, I am a big fan of EOF. EOF would make my life much easier. That would be fantastic. Yeah.
Okay, any more questions? Then I have just one. I think near the beginning you mentioned something about how Daphne EVM supports up to the Berlin fork, but no subsequent forks yet. Is there a way you can give some idea about what's the kind of, why you stopped there? Like, why no further? Is there some big road, like hump to get over?
No.
Okay.
No. It's simply because, I had to draw the line somewhere and I wanted to focus more. Like we have a small team. I wanted to focus more on actually using it and finding out the problems from using it. Yeah. To be honest, pretty straightforward to update to new forks. That wouldn't be a problem. The only real challenge is that we didn't build it from the outset to support multiple forks, so I just need to put that kind of support in to switch between them, but otherwise, it's not a big problem, no.
Understand. Okay, well then, thank you very much.